what is resonance and what is aromaticity, which imparts benzene its unique character, its unique stability, its unique set of reactions. Let us understand the concept of resonance and aromaticity. Sometimes multiple chemical structures in which electrons are shared between just two atoms can be used to represent a single molecule. Means a molecule can be represented by multiple chemical structures or structural formulae, and you can call them as a canonical forms or resonance forms. And in these cases, no single such structure is correct, and but the combination is rightly explaining the structure, and this particular thing imparts the molecule very special stability, very special chemical properties, especially for certain cyclic systems. What is the reason? This reason lies under two concepts, resonance and aromaticity, and in this lecture we are going to see what is resonance and what is aromaticity. Let us consider the acetate anion. The resonance structures for acetate anion can be represented. In one case, the negative charge is on this oxygen, other case it is on this oxygen, and what has happened is the double bond has changed its position. When two chemical structures involving electrons shared between just two atoms may be drawn to represent that molecule, the molecule's true structure is intermediate between them. Means it is neither this single alone or this single, it is an intermediate. What is that intermediate? We will see in the end. The contribution from multiple hypothetical structures to the true structure of the molecule is called as resonance, and such structures are called as resonance forms or resonance structures. And the intermediate structure which evolves out and which is true is called as a resonance hybrid. Resonance often results in the presence of electrons which cannot be assigned to a single atom or bond. You cannot say it is here exactly, it can be here also. That is why we are suggesting two structures. A resonance hybrid, so these electrons cannot be localized, they are delocalized. A resonance hybrid is always more stable than resonance structures or canonical forms that contribute to it, and it is this phenomenon which is known as resonance stabilization, and this is a resonance hybrid. So you can say the electrons are spread over here. Electron is such a fast moving entity, you cannot say it is in this place. So that is why we came to a concept of orbital. Now let us understand, after understanding what is resonance in a very simplified manner, now let us understand in equally simplified manner the concept of aromaticity. A conjugated system, that is a system possessing alternate double bonds, is a chemical system or structure bearing a series of alternating single and double bonds, meaning there is a p orbital on each atom. Owing to resonance, in conjugated system of alternate bonds, the double and single bonds are able to switch the places. Means at one structure it can be a single bond, in another structure it has become a double bond, and vice versa, producing an overall more stable structure. Conjugated systems can also exist in cyclic molecules, and here the concept of aromaticity arises. A conjugated cyclic system which is stabilized by resonance is called as an aromatic system. So it's a conjugated cyclic system. Understand this. A classic example of an aromatic system involves a six-membered ring, and that is our benzene ring. So this a conjugated cyclic system which is stabilized by resonance is called as an aromatic system. So this is the definition of aromaticity. These are some simple structures having alternate double single bonds. Okay. and this can be written like this. Each carbon has got a p orbital. These are also alternate double bond, single bond systems or conjugated systems, but they are all not aromatic because they are not cyclic systems. But here we have a cyclic system which is furan, carbon, 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 oxygen. And you have an electron pair here, electron pair here, electron pair here, which take part in the resonance. This does not take part. Okay, this is not taking part in the overlapping because it is in different plane. So 6 electrons are participating or they are in conjugated system. This is furan. So let us see the resonance in benzene and its derivatives. This is the classical Kekule structures, alternate, double bond, single bond. And this is the resonance hybrid benzene. Benzene and other aromatic compounds exhibit a chemistry which is very different than ordinary non-aromatic compounds, and to distinguish between them and non-aromatic compounds which are often labeled as aliphatic compounds, benzene and other aromatic compounds can have substituents, or sometimes benzene itself is a substituent. It is called as a phenyl group. Let us now come to what is aromaticity and what is Huckel's rule. 4n plus 2 rule also is the other name for it. Benzene is unusually stable, and this stability seems to be correlated with the carbon 2 particle, orbitals to form the pi molecular orbital. Ehrlich Huckel proposed a criteria for this sort of stability, which is called as aromaticity. A compound is said to be aromatic when it meets all the 4 following criteria. Please understand these 4 and remember these 4 criteria of aromaticity. This comes as a short note. Aromatic compound consists of one or more rings that have a cyclic arrangement of p orbitals. Thus, aromaticity is a property of certain cyclic compounds. Every atom of an aromatic ring has a p orbital. This is another criteria. Every atom has a p orbital. Aromatic rings are planar. They are flat planar rings. Cyclic arrangement of p orbitals in an aromatic compound must contain 4n plus 2 pi electrons, wherein n is a positive integer 0, 1, 2, and n stands for the number of rings. So in benzene, n is 1. In other words, an aromatic ring must contain 2, 6, 10, 14 pi electrons. These are collectively called as Huckel 4n plus 2 rule or simply 4n plus 2 rule. Benzene with 4n plus 2, because it n is 1, shows that the aromatic compounds take 4n plus 2 electrons to fill exactly the bonding orbitals of pi electron system. Therefore, criteria number 4 is satisfied. Each double bond contributes to 2 pi electrons. We see more examples of such aromatic compounds. Benzene, if 2 benzene rings are joined to each other, it becomes naphthalene. So N becomes 2, 4N becomes 8 plus 2, that is 10 pi electrons. If 3 rings are joined together, then N becomes 3. So 4 3s are 12 plus 2, 14 electrons. So this is naphthalene, 2 rings. So 8 plus 2, so 10 pi electrons. Anthracene and phenanthrene, 3 rings. 4 3s are 12 plus 2, 14 electrons. Aromaticity is defined as the ability to sustain induced ring current by a flat or nearly flat cyclic system with 4n plus 2 delocalized pi electrons. Some more examples is toluene. This methyl ring does not participate in the aromatic system, but the benzene is definitely aromatic. So toluene as a whole is aromatic. 1,3,5 hexatriene. Is it aromatic? No, it is not aromatic. Though it may contain 6 pi electrons, it fails in the criteria for aromaticity, that is criteria number 1. It is not cyclic, and an aromatic species has to be essentially cyclic. To summarize aromatic characteristics, the characteristic property of aromatic compounds are they have low heat of hydrogenation, they undergo electrophilic substitution reactions, they are resistant to addition reactions like alkenes, alkynes, etc. They are flat molecules, and most importantly, they should contain 4n plus 2 pi electrons or Huckel's 4. They should follow the Huckel's 4n plus 2 rule. So these have aromatic systems have special chemical and physical properties. Though unsaturated, they undergo electrophilic substitution reactions rather than addition reactions. They are resistance to they show resistance to KMnO4 or HNO3 oxidation. They exhibit unusual thermal stability with very low heat of uh, hydrogenation and a low heat of combustion, and they have unique nuclear magnetic resonance properties, a very typical place. They all exhibit their hydrogens, benzene hydrogens will exhibit a very peculiar phenomenon in or observation in NMR. The spin-spin coupling signals will be particularly all coming together in a particular region where somewhere around 8 ppm. So before I end this short session, please comment on the structure of benzene in details, comment on the stability of benzene and what is stabilization by resonance, and discuss the concepts of resonance and aromaticity with suitable examples, and what is meant by Huckel's 4n plus 2 rule, and what is the criteria for aromaticity, what is its basis, explain with suitable examples. So thank you very much.